Deutsch algorithm. So I'm going to try to go through that and sort of understand the algorithm and the way it's built, and then see what kind of takeaways can we take at the intuition level for quantum computing in general, quantum programming in general. I think that's a really good thing to do, especially because that's going to put all that I've been learning into a more pragmatic dimension, and then see if we can see what happens, right? I mean, I'm really curious about how is it gonna all go. So I see some maths in here, but some circuits as well. So I think that's gonna be interesting. Let's get going. So the deutsch-jozsa algorithm was the first example of quantum algorithm that performs better than the best classical algorithm. That's interesting. So it showed that there can be advantages in using a quantum computer as a computational tool for a specific problem. The algorithm solves the following problem. Suppose that you're given a function 0, 1, 1, 0, 1, which takes 0 or 1 as an input and outputs 0 or 1. The function itself can be as complicated as needed. The only requirement is that it takes a bit as input and it outputs another bit. Okay. Given the two different inputs, so I sense it's still going to be a bit abstract in terms of that's not an actual, maybe an actual problem, but we'll see. Maybe that will help me connect a couple of dots here and there, and then get something out of it. So given two different inputs, x and y, check if the function fx is equal to fy. Let us first see. So that's the problem, I guess. Let us first see how the classical algorithm solves the problem. The best way to do this classically is to evaluate fx and fy separately and then compare the results. This requires at least two calls to the function f. Correct. So you call fx and fy and then you compare. The deutsch-jozsa algorithm can solve this problem in only one step. Quantum circuit for deutsch-jozsa algorithm. The quantum circuit, okay, so we see a Hadamard, we see a measurement, and then we have this Q thing here, so the H are Hadamard gates, and QF is the query function described by the action on a qubit X. Is the query function described by the action on a qubit X as... So this seems to indicate has to do something with, so it takes this qubit and then turns it into that. That's what that gate is supposed to do, which seems like it has to do with flipping the sign to a minus. Let's see. I gotta learn maybe the shortcuts for that. So now let's go through the steps of the algorithm. The input qubit is initialized to the 0 state. Good, easy. We apply Hadamard on the qubit to get the state. Yeah, so we get basically a superposition of 0 and 1, as in it's 50% 0 and 50% 1. Then we make the query QF. Okay, so here they are applying directly so what it seems like it's minusing F0 and F1. I guess the 0 here is because of the qubit 0, and the 1 here is because of the 1. I mean, it's because of the state 0 and the state 1. So it seems like you could technically say that it's applying that function to both, because we have it in the Hadamard, because we've applied the Hadamard. Let's see. It's going pretty fast, so I don't know. This, if F0 equals F1 up to a global phase factor, then we've got that. And if it doesn't equal, then we get that. I'm not sure I understand this here. Apply Hadamard again. So if f0 equals f1, then we get that. And if it's not equal, then we get that. So you measure the qubit and you get a 0 or 1, whether they are equal or not equal. Oh, interesting. Therefore, by looking at the value of the measured qubit, we can tell whether f0 equals f1 or f0 doesn't equal f1 by solving the problem with only one query to the function compared to the classical algorithm. Also, if the input of the function is not just one, this might not seem much of an advantage, but yeah. Also, if the input of the function is not just one bit but an n-bit string, it can be proven that the quantum algorithm will take n divided by 2 queries to the function. Just run the algorithm on a pair of bits rather than n steps needed for a classical algorithm. And then we've got an example. Okay, if the algorithm was implemented on a real device, however, in order to do it, 2 qubits were used. And one is used as an ancilla qubit. An ancilla qubit is an additional qubit that is used in the quantum computation. In this way, the query function was realized. Let us see how it works. So the first, okay, so that's kind of more the practical implementation. The first qubit is initialized to 0, and the second is initialized to 1. Okay. You apply the Hadamard in both qubits, and then you get that thing here. So this is a superposition of all possible combinations with equal probability. That's kind of what's happening here. The query function QF can be implemented in different ways. Let us consider the case where f0 equals 0 and f1 equals 1. This QF is a control knot on the qubits 1 or 2. Oh. Okay, so basically what's happening is to prove that, so the thing is QF has to be hard-coded in the quantum circuit. The function has to be hard-coded in the quantum circuit. So it's kind of, yeah, not so much practical, I would say, but it probably serves the purpose of illustrating that you can solve the problem with just one run, with just by querying that just one time. The query function can be implemented in different ways. That is considered in this case exactly. So, yeah. Wow. And applied Hadamard in both qubits again, and then measure. And then we've got a Qiskit implementation already. And you can draw the circuit. Experiment with simulators. And that's it. And that's it. That's all the explanation. Yeah, obviously, in a real device, you're never going to have like a clean, 100% probability 1 or 0. So you're going to have something like that. And then by running the same thing like 1,000 times, then you're going to kind of see that that's the result you get the most, right? But I'm trying to understand a bit what's the sort of underlying principle of this algorithm, which is really simple at first sight. So basically, let's go back to that part, which is the more theoretical. Because what it's saying is we have a function, and so we have a function, right? And let me change colors. So we have a function here, which is this thing here, and then what we're saying is you can encode that function in the quantum circuit. So Okay, so apply the Hadamard and then make a query. So the thing is, the way you apply the function is not by applying the function, but by applying it as an exponential to a -1, right? So what this is telling you mathematically is that if so if f0 equals f1, if f0 equals f1, then you can then you end up with this state here, and if it's unequal, you end up with this state here, right? Because that's your, here's your starting point. But why is that correct? Because I mean, is it just given in the problem? Yes, I think that problem function f. Okay, so it is in the problem that the function can only take 0 or 1 as an input and 0 and 1 as an input, because that's so it seems to me this is basically exploiting the structure of the constraints of the problem, right? Or of the problem. So it's basically saying, because of these properties, this is possible. So it's only f0 and f1, right? So and if they are the same, so this means they're either both zeros or both ones, then you're going to end up with -1, -1, -1 here, -1 here, so you can abstract it, and then you get that state. That makes sense. But if they are different, so if one is, sorry, I mean, if they're both zeros, they're obviously plus +1. So you can abstract it away anyway. Yeah. I mean, if they are different, then you're going to have, then you only can do that if you leave the minus here mathematically. Yeah. Yeah, of course. So which then brings you to this here, right? So which is basically saying, well, it leaves you with this here once you apply a Hadamard, because basically if you apply a Hadamard again here, right? So what the algorithm is doing is you move the you get into a Hadamard, like into a superposition state. Then by applying the function, you're transforming your state in a way that when you apply the Hadamard again, because the Hadamard behaves in a way that that it's going to turn that into a 0 and turn that into a 1. That's how the Hadamard essentially works. So exploiting, basically, it's sort of a combination of exploiting the way the Hadamard gate works, and yeah, it's difficult to take something out of that at an intuitive level, but I understand the algorithm, right? So it's basically saying, well, we get into so we bring the uncertainty in our dimension, right? And it's playing with the fact that when you apply the Hadamard gate, when you apply the query, so when you apply that function, it basically, at the end of the day, those two states would measure the same. If you just measure here, you would get with 50% chances a 0 or a 1 in both cases. It's just that there's this little phase here, there's like a minus here. So this means that when you apply a Hadamard gate again, then you end up in different states. So let me walk a little bit back. So go a little bit back. So what this is doing at an intuitive level is manipulating uncertainty it's manipulating uncertainty in a way that then when you measure when you move it around, ooh, it's complex. It's complex. It's like a super simple problem, obviously, um, but basically it's taking advantage of the superposition. It's taking advantage of the superposition and the fact that this is an uncertain state, and you can play with that. So if you apply a function into a state that is both zero, it could be both 0 and 1, you're virtually applying the function to, you could say you're applying it to all possible states. But it's exploiting, you see, it's exploiting essentially the fact that the function can only give you a 0 and a 1, and that cannot take 0, and it can only take 0 and 1 as an input in this case. So and it's using that as the exponential of -1. So it's designing the function and encoding the function in this in the circuit in a way that it's gonna manipulate the uncertainty and exploit the structural properties of the qubit. Not structural, but maybe the actual quantum physics, quantum mechanics, quantum mechanic effects. Yeah, it's still a bit abstract, but it's a good starting point. I'm curious because it says you can try that with with an n-beat string. With an n-beat string. Okay. Interesting. So it's using basically, yeah, interesting. Applied Hadamard, and that's kind of practical implementation, and that's only practical in this case because of the way I guess if you would like to play that with a different function where f0 equals 0 and f1 equals 0, then you would not implement the control knot in here, right? So that's just that's just because of the example that we're implementing in terms of the function that we're implementing. Okay. I'm not going to go through the details of how you implement that with Qiskit right now, but basically, it's an interesting example.